This week is on the electric potential, and there's a second chapter um, in the textbook by Bauer and Westphal. It's chapter 24 on capacitors. And capacitors are related to the electric potential. So chapter 23 and chapter 24 are sort of combined this week. So you'll have the book to study, but I want to give a quick preview of the topics having to do with capacitors. So we'll start with sort of an introduction. In general, a capacitor is a system with two insulated conductors which have equal but opposite charge, plus Q and minus Q, and a potential difference. So we could say V2 minus V1 is equal to delta V. So here's an example, just two spheres with equal but opposite charges, plus Q and minus Q. You know there'll be an electric field filling the space around these two spheres. Now, these are conductors. And in electrostatics, the electric field inside a conductor is zero. So that means the electric potential inside a conductor is constant. In other words, a metal in electrostatics is an equipotential region of space. So in this positively charged sphere, every point has the same value of electric potential. Call it V2. So V2 is the electric potential of this sphere. Not any particular point in the sphere, all points in the sphere. And similarly, this second sphere has charge minus Q. All the points in that sphere have the same potential, V1. And now we'll define delta V as V2 minus V1. V2 is the potential of the positive charge. So that will be greater than V1, which is the potential of the negative charge. Remember, the electric field is the rate of change of potential. So, well, it's the rate of decrease of the potential. So in this sphere, we have higher potential. In this sphere, we have lower potential. Well, that's a general, kind of a theoretical definition of a capacitor. But actually, capacitors are very important in electrical engineering and in electric circuits. In practice, this would not be the form of an electric, of a capacitor in a circuit. So in practice, a capacitor is a device that's used in circuits. A capacitor is a device that stores charge and energy. It often takes the form of two plates or two metal foils close together and insulated from each other, so separated by some sort of insulating material. Here I show two metal plates with just vacuum in between the two plates. The insulating material there is just vacuum. And there'll be an electric field which is concentrated in the region between the two plates, especially if they're close together. And we'll see in a little while that to make a large capacitance, the plates should be close together. One plate has potential V2. It's a metal, so every point in the plate has that same potential. The other plate has a potential V1. And if this is the positive charge, that'll be the high potential. The negative charge will be the low potential. So this is what we call a parallel plate capacitor. Now in realistic circuits, you'd actually have not solid plates, but metal foils close together, probably separated by some insulating material. Could be something as simple as paper. And those two foils are sort of rolled up and put in a cylinder, put in a can. So it would be unusual to have well, it's not impossible. It's not really all that unusual, but for a large capacitance, more likely you'd have metal foils and not maintained as planes, but rolled up in a kind of a spiral. That would also be considered a parallel plate capacitor. So it's not necessarily a solid plate, could be a metal foil. And a lot of the lawn kappa problems will involve exactly this kind of capacitor. Now you see the geometrical parameters of a parallel plate capacitor are the area, so that's A. They're two plates of equal area. We both have the area A. And the separation, distance D. So they're separated by some distance D, which is normally very small. So D is small compared to the square root of the areas. And one of the derivations you'll find in chapter 24 is the formula for capacitance of a parallel plate capacitor in terms of A and D. The capacitance, I have to define, the capacitance will be a ratio involving charge and potential. But the charge and the potential are proportional. So when you take the ratio, the charge cancels out, and you end up with a quantity that only depends on the geometrical parameters. Okay, now the parameter that describes a capacitor is called the capacitance. And, well, I have here two equations for capacitance. They have different meanings, though. The first equation here is the definition. So this is the definition of capacitance. Remember, a capacitor has two conductors, equal but opposite charge, plus or minus Q. So plus Q, minus Q, and potential difference delta V. All right, so the definition of the capacitance is Q over delta V. So it's the charge of the capacitor divided by the potential difference between the two conductors. I have to be a little careful about the language. The charge of a capacitor, the net charge of a capacitor is zero. Overall, the capacitor is not charged. But we say the capacitor is charged because charge is separated into two parts. A positive part, plus Q, and a negative part, minus Q. So Q here is not really the charge of the capacitor, although it's often called the charge of the capacitor. It's the charge of the positive plate of the capacitor. The net charge is 0. So Q over delta V is the definition of capacitance, and that's a very general form. That holds for a capacitor of any design. Now, the second equation says the capacitance is epsilon naught A over D. Well, that's not a general equation. That's a specific case. That's an example. That's the case of a parallel plate capacitor. A parallel plate capacitor has two parameters: the plate area and the separation between the two plates. So this is the separation. This distance is D. And so these two equations have very different meaning. This is a general definition. This is a special case of a parallel plate capacitor. And you'll need both of these equations to do the long kappa assignment. So I hope you're taking notes. Now, why is this the correct formula for capacitance in the case of parallel plates? Well, let's analyze the electric field between the plates. I really think of D as being small. So the two plates are very close together. Therefore, the electric field is concentrated in the volume between the two plates. There's a little bit of electric field that leaks out around the sides, but the predominant part of the electric field is concentrated between the two plates. So let's analyze this definition in terms of the electric field. We have this definition. C is Q over delta V. Now, the electric field is delta V divided by D. Remember, the electric field is the rate of change of the potential with respect to space. So if I take the change in the potential divided by the distance over which the change is occurring, I get the electric field. Or another way to see this is that the change in potential is the line integral of E dot ds. Well, the line integral of E dot ds will just be E times D. Because the electric field between the two plates is a constant, and the distance between the two plates is D. Now apply Gauss's law. Set up a little Gaussian surface here in the shape of a can that cuts through, well, that the lower plate cuts through the center of the can. Now, the electric field is predominantly between the plates. So there'll be a flux through this upper surface. There'll be negligible flux through the lower surface, because that's outside of the region between the plates. So there's essentially zero flux, where down here the electric field is 0. So the flux through this Gaussian surface will just be the electric field times the area of this top part of the Gaussian surface. Call that area A. That's not really the full area of the plate. That's just the area of this little end of the cylinder. So here's the flux, E times A. And Gauss's law says that's Q over epsilon 0, where Q is the charge enclosed by the can. The only charge enclosed by the can is the little portion of Q in this area. So it's a fraction of Q. It's Q times A divided by the full area. So it's the fraction of Q inside the small area A. So that'd just be Q divided by A times the small area A. In other words, Q divided by little a is the same as capital Q divided by the complete area. This is charge per unit area. Well, it's uniformly distributed. The charge is uniformly distributed over the plate, so that's the same as the complete charge over the complete area. All right, now let's put all this together and calculate C. C is Q over delta V. Delta V is E times D. So it's Q divided by D times E, and by this equation, E is Q divided by A divided by epsilon 0. So I have Q divided by epsilon 0. This really should be epsilon 0, A, E. It's Q over epsilon naught A times D. And now finally, capital Q divided by little q is capital A divided by little a. So I can replace Q divided by Q by A divided by little a. So then I have A in the numerator. Here I have 1 over epsilon naught in the denominator, so that's epsilon naught in the numerator. Should be epsilon naught. And here I have 1 over A times A. So the A's cancel, and I just left with D in the denominator. So that's the derivation of this result. And you see, it's peculiar to parallel plate capacitors. There will be problems where you have a different shape for the capacitor, and you have to use a different formula for the capacitance. Okay, now here are some of the things that you'll need for the Kappa problems. In section 3, the capacitance for a cylindrical capacitor or a spherical capacitor. I derived the capacitance for the parallel plate capacitor, but what if you had a capacitor in the shape of a coaxial cable, a cylinder inside another cylinder? That's a problem which is given in section 3. Section 4 is on capacitors in circuits. So what happens if you put a capacitor in a circuit? Let's say you have a circuit with a capacitor and a battery. So here's a battery. Well, the potential difference of the battery will be the same as the potential difference across the plates, and so the plates will be charged up. One side positive, the other side negative. Section 5 concerns the energy stored in capacitors. And I'll talk about this in a minute. Section 6 consists of capacitors where the insulating material between the plates is not vacuum, but a dielectric. Then the capacitance is not epsilon 0 A over D, it's epsilon A over D, where epsilon is the dielectric constant. That's the dielectric constant for the material that you put between the plates. Epsilon 0 is called the permittivity of the vacuum. Epsilon is sometimes called the permittivity of the material, or could be called the dielectric constant. So to do the Kappa problems, you'll have to understand some of the equations in chapter 24. All right, now I mentioned the energy stored in a capacitor. A capacitor separates positive and negative charge. So that stores up charge. And there's an energy stored in the capacitor. We call the energy U. And according to field theory, it's energy of the electric field in the space between the two plates. So let's derive some equations, which again you'll see in some of the law and kappa problems. First of all, let's calculate the energy stored in a capacitor. So let's think of it as a parallel plate capacitor. That's the simplest way to think of it. You have, let's say, charge minus Q on one plate and charge plus Q on another plate. And there'll be an electric field between the plates, and there'll be a potential difference. The electric field points from the positive plate to the negative plate. The electric field is the rate of decrease of the potential. So the negative plate will be the low potential. The positive plate will be the high potential. The electric field points from high potential to low potential. All right, now let's start with this point, and now let's increase the charge. Let's move a little bit of positive charge from this negative plate, making the negative plate even more negative, and making the positive plate even more positive. So let's increase the charge separation by moving a little bit of charge from the negative plate to the positive plate. So let's call this charge dq. It's a little bit of charge, a little bit of positive charge we take from the negative plate and put it over on the positive plate. All right, so we start with the charges plus Q and minus Q. Now move an additional charge dq from the negative plate, what's wrong, to the positive plate. Well, I'm moving that charge to a higher potential. So I'm increasing the potential energy. The change in the potential energy, let's call it du, is the amount of charge times delta V. Remember, that's one of the ways to define potential. It's potential energy per unit charge. Or potential energy is charge times electric potential. So if I'm moving this charge from the low potential side to the high potential side through a potential difference delta V, the increase in the potential energy is dq times delta V. Now remember, delta V is Q over C. That's the definition of capacitance. Capacitance is Q over delta V, or delta V is Q over C. Now you see I have here, well, C doesn't depend on Q. Remember, C is a constant as far as Q is concerned. So what I have here is the differential of Q squared. Actually, Q squared over 2. Remember, the differential of x squared is 2x dx. You know, the derivative of x squared with respect to x is 2x. So the differential change in x squared is 2x dx. So differential change in q squared is 2q dq. Well, let's divide by 2, so the 2 will cancel, and I'll get q dq over c. So in other words, this change in the energy is the change of q squared over 2c. And that tells you that the energy is q squared over 2c. Now this tells you the change in the energy. But of course, if q were 0, there would be no energy. There'd be no field between the plates if q were 0. So if Q is 0, U has to be 0. The change in U has to be the change in Q squared over 2C. So U has to be Q squared over 2C. Or I could write it in this form. I could write it as 1/2 C times delta V squared. Because remember, delta V is Q over C. So this would be 1/2 C Q squared over C squared, Q squared over 2C. All right, so that's the energy stored in a capacitor. Now, the other equation I wanted to derive is the energy density of the electric field. You know, you have some electric field present. It fills up a region of space. At each point in space, there's an electric field vector. Suppose you took a little volume in the space and you wanted to know how much energy is in that volume. Well, it would be the energy density times d3x. If that volume is d3x. So, in other words, energy density, we'll call it little u, lowercase u. Energy density is the energy per unit volume at a point. Energy per unit volume, that's energy density. And, you know, the electric field can vary at different points in the space, so you have energy density as a function of position in the space. All right, now let's derive a formula for the energy density of the electric field. Start with a capacitor. The energy is 1/2 C times delta V squared. And let's specialize it to a parallel plate capacitor. So the energy will be 1/2. C is epsilon naught A over D. Delta V is E times D squared. So I have here A times D squared over D. I have A times D, epsilon naught over 2E squared. And A times D is the volume. You know, if you have a area A and a height D, then the volume of the space between the plates is A times D. So the energy density is U divided by volume. It's the total energy divided by the total volume. For this case where the electric field is constant. So you see we get the result, epsilon naught divided by 2E squared. So that's the energy density derived from a parallel plate capacitor where the electric field doesn't depend on position inside. But this is the correct equation for, you know, it only depends on the electric field. So if you had an electric field that was different at different points in space, then you'd find the energy density at a point in space is just the square of the field at that point. So this is a very profound equation. It relates electric fields to energy. The energy per unit volume, the energy density, is 1/2 epsilon 0 E squared. Goes like the square of the electric field. And we'll see applications of that throughout the semester. We'll have a similar equation for magnetic fields. The energy density of a magnetic field goes like the magnetic field squared. And also the energy in light, because light's an electromagnetic wave. So this will be an equation that's used later in the course as well. And I think there's probably a law and kappa problem that relies on that too. All right, so that completes part 2 of the screencast, the part about capacitors and capacitance. Now these have just been theoretical derivations. There'll be another part of the screencast, part 3, which gives some examples similar to the problems that you have on the law and kappa assignment.